Now that we understand coordinates relative to a basis, we can come back to the question of finding a matrix that represents a linear transformation when the domain and or range is not an entire Euclidean space. So suppose we have such a transformation from V to W, and we have a basis V1 through Vk for V, and a basis W1 through WL for W. That's an L right there. So to get a matrix, we have to have a linear transformation between Euclidean spaces. But it can't be the Euclidean spaces that contain a V and W, because the linear transformation isn't defined on those Euclidean spaces. So instead, it should probably be the Euclidean spaces that the coordinate transform relative to the basis sends V to, so that's going to be RK, and also W, and that's going to be RL. So T is a transformation on this side from V to W, and you can see we almost have a transformation from RK to RL. All we need to do is replace the coordinate transform for the basis V with its inverse, right? Remember, it's 1 to 1. It's also clearly onto, so it has an inverse. In fact, let me move this over here. Okay. This coordinate transform from W to RL also has an inverse, but it turns out we're not going to need that inverse. And just to make it explicit, remember that this, over on the V side, this is the transform that if you have the matrix with the V's times a vector of coefficients, the coordinate, no, this is inverse here. The coordinate map sends this to just the vector of coefficients like this. And the inverse takes the vector of coefficients and sends it to this matrix product. Remember, this matrix product is really just A1, V1 plus dot, 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 up to A, K, V, K, right? Okay, and over on the W side, the transformation, the coordinate transformation relative to the basis for W, that's the transformation that takes, right, if you have the W's, W1 through WL, times some vector of coefficients, let's call it B1 through BL. This coordinate map sends this to the vector of the coefficients, so B1 through BL. Okay, so starting in RK, doing this inverse coordinate map and then T, and then the coordinate map over on the W side, the composite is a linear map from RK to RL. So that means that there's a matrix that represents this linear map. So I've called it A here, but keep it. Maybe I shouldn't have chosen A for these entries here, because these A sub 1 through A sub K, these are not the entries of the matrix A. So how can we find the matrix A? Well, we just need to see what this linear transformation is. So if we start with a vector of coefficients in RK, A1 through AK, right, this gets sent to A1 V1 plus dot 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 up to AK VK, which, remember, this is the same thing as V1 through VK packed into a matrix times the vector of coefficients A1 through AK. Okay, what does T do to this vector? Well, it sends it to t of a1 v1 plus dot 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 up to ak vk. But by the linear transformation property, this is the same as a1t of v1 plus dot 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 plus akt of vk. But you know, this linear combination of the t of v whatever, this is actually the same thing as t of v1 up through t of vk packed into a matrix times the coefficients a1 through ak. Okay, so that's what the linear transformation does to, or that's what t does after we do this inverse coordinate map first. Now we need to take this result of t and see what this coordinate transformation does to it, right? What coordinates it gives us in RL. But to do that, first we have to write this vector that we have in terms of the basis, the W basis, right? Because to know what this coordinate map does, we have to have it written as a matrix full of W's times some vector. And then the coordinate map produces just the vector, right? It sort of throws away the W's essentially and just keeps the coefficients. So to know what the result of this is, we have to have this written in terms of the W's. So that's kind of the tricky bit. Well, t of v1, since the W's are a basis, so this is in the space capital W, right? The subspace capital W, but the W's act as a basis for this space. So so we can write this as a linear combination of the W's. So it's W1 times some coefficient. I guess we've used A's and B's, let's call it C. So what subscripts to use, I'm gonna leave that. We'll decide how to arrange the subscripts in just a second. Okay, up to W, L, C, something. Okay, so how should we arrange the subscripts? You can see we're going to have one subscript depending on what V we're talking about, and another subscript depending on what W we're talking about. Well, the subscript on V, that's acting like a column subscript, and you can tell that because look, here it is acting like a column subscript. So that means the column subscript for all of these C's should be 1. So like this. Now the subscript on W, right, which is going from 1 up to L, that's also a column subscript. You can tell because up here we have, right, the subscript on W telling you what column you're on. So this subscript on W is also a column subscript, and column subscripts get summed against row subscripts. So if it's column 1, the corresponding subscript should show up in the row position for the coefficients, all the way up to WL C sub. So the row subscript should be L times 1. Okay, and then there's one equation like this for every t of v whatever, so up to t of vk. That's going to give us W1 C sub. So first subscript matches the W, so 1, and second subscript matches the V, so K, plus dot dot dot, up to WLCLK. Okay. Now, the way we have this set up, we can actually write down all of these equations all in one go by packing the left-hand sides into a matrix. So just treat each one of these left-hand sides as the column of a matrix. So T of V1 up through T of Vn equals, and now if you look at this right-hand side, this is actually the matrix that we get from packing all the W's into a matrix times C11 up to C1k. Sorry, I have an n here. This should be v sub k. And then down to CL1 up to CLK. All right. Now we can check that this is correct, because if we take this matrix with the W's and do the matrix product with just the first column from the C's, we should get the first column on the left-hand side. And if you do this, you get C11 times W1 all the way up through CL1 times WL, but that is this first row, right? So that is T of E1. So all of these equations, we can express them compactly with this matrix equation. And this is really nice because it tells us this matrix whose columns are the results of T applied to all of the V's, it expresses them as W's times some coefficient matrix. This is actually exactly what we needed to evaluate the coordinates relative to the W basis. So what we'll do is take this expression for this T sub V1 through T sub Vk, take this and plug it into that equation, or that formula we got up above. So that was up here, right? So another way to write this is W1 through WL times our matrix of C's. So rather than write it all out, I'm just going to write Cij. So that's this first bit. And then the rest of it that we need to write down are these coordinates, A1 through AK. Okay. Now that we have this written in terms of the W's, the coordinate transform just kind of throws away the matrix with all the W's and keeps the stuff that's left. But the stuff that's left is the C matrix times the vector of coefficients A1 through AK. So here we had a linear transform from RK to RL. We started with A1 through AK. We did this transformation and we ended up with the C matrix times A1 through AK. So that's just a fancy way of saying that this matrix that represents this transformation is Cij. So this matrix, the C matrix, is the one that we're looking for, and it's really doing double duty. On the one hand, this C matrix, when you multiply it on the right, or when you multiply by it, when you multiply the W matrix by the C matrix on the right, what you get is the result of the linear transformation. But on the other hand, if you have coordinates for V relative to the V basis, if you multiply that on the left by the C matrix, you get coordinates for the W basis, the coordinates of the result of the transformation for the W basis. So this C matrix is really, it's really doing double duty. This whole thing also tells us how we can find the C matrix. Right? The C matrix comes from this equation right here. So to find the C matrix, right, in any particular situation, we will know or be able to find these output vectors from the transformation. We will have some basis in mind, so all the W's we will know. And so this is just some big matrix equation that we need to solve. So let's look at an example of actually finding this C matrix. All right, so here's a linear transformation from V to R3, and V is the span of these two vectors. These two vectors are clearly linearly independent because they are not multiples of each other, right? Two vectors that aren't multiples of each other are linearly independent. And T is defined on this basis, so this defines a linear transformation on all of V. So let's find the matrix for T relative to this basis that we have for V and relative to the basis for R3 that is these three vectors, 1, 2, 0, minus 2, 3, 0, and minus 4, 1. So remember, to find this matrix, right, the matrix that we're looking for is just that C matrix that we had before, and that is the solution to this equation. So we need to take our output, so the basis, here's V1, here's V2, and then these three, these are the W's, W1, W2, W3, and W is just R3, all of R3 in this case. So what we need to do is take this equation, T of V1 and T of V2, pack those into a matrix, set that equal to W1, W2, W3, right, the basis for our range space, times our C matrix. And in this case, the C matrix is going to be 3 by 2. So it's 3 C11, C21, C31, C12, C22, C32. So we get this matrix equation. We just need to solve this matrix equation. This is going to be doable because this matrix right here with the W's in it, this is 3 by 3, and since the W's are linearly independent, this matrix is going to be invertible. So we can find the inverse and then use that to solve this equation. All right, so let's just write this equation down explicitly. T of V1 is given up here, so that's 2, 0, 3. T of V2 is 0, 1, 4. All right. So now our matrix of W's, actually let me leave some space here for the inverse. So our matrix of W's is 1, 2, 0, minus 2, minus 3, 0, minus 4, 1. And then Cij. All right, now to solve this, we can just find the inverse for this matrix and multiply on each side of the equation, multiply on the left by the inverse of this matrix. So I figured this inverse out ahead of time. It is minus 3, 2, minus 4, minus 2, 1, minus 4, and 0, 0, 1. So we need to multiply on the left by that on both sides. So minus 3, 2, minus 4, minus 2, 1, minus 4, 0, 0, 1. Okay, and then work this out. So on the right-hand side, these two matrices are inverses, at least unless I made some mistakes. These two matrices are inverses, so when we multiply them, we just get the 3 by 3 identity. So the 3 by 3 identity times this C matrix just gives us the C matrix. So to work out the C matrix, we just need to do this matrix product here. So let's see, 2, 0, 3 times minus 3, 2, 4. So minus 6, minus 12, that's minus 18. And then minus 4, minus 12, that's minus 16. And then 3. And then for our second column, 2 minus 16 is minus 14. And then 1 minus 16 minus 15, and 4. So there's our matrix, there's our C matrix. So how could we have some confidence that this matrix is doing the correct thing? Well, remember, this is the matrix that you multiply V coordinates by to get the output of the transformation in W coordinates. So let's take this vector in R2, yes, this vector in R2, and let's think of this as V coordinates. So as you know, what vector would produce this 1, 0, or I'm sorry, 1, 0 as coordinates for a vector in V, well, that's just going to be V1, right? V1 is 1 times V1 plus 0 times V2. And so the coordinates for this vector relative to the basis of V1 and V2 is just 1, 0. Okay? So to see what the linear transformation does to this vector, we multiply this on the left by our C matrix. So minus 18, minus 14, minus 16, minus 15, 3, 4. So times our coordinate vector. And this matrix product is easy. That's minus 18, minus 16, 3. So what does this tell us? Well, remember, this is the coordinates. It should be the coordinates for t of v1, right? Since the t of v1 was the vector whose coordinates are 1, 0. So this should be the coordinates for t of v1 relative to the basis w1, w2, w3. Okay, so how could we check if that's right? Well, let's use these entries as coefficients for this basis. So minus 18 times w1 minus 16 times w2 plus 3 times w3. And if this is right, so if this matrix really is the C matrix we were looking for, then this linear combination should be T of V1, right? Because the coordinates for V1 should have been turned into the coordinates for T of V1. So if these are the coordinates for T of V1, then when we use them as coefficients for our basis, we should get T of V1. So let's actually compute this. The size of these numbers makes me a little nervous because it means I'm going to have to do work with some large numbers, which is always unfortunate. So 1, 2, 0 minus 16 times our second basis vector minus 2, minus 3, 0 plus 3 times our third basis vector is minus 4, 1. Okay, so let's see. Here's 18 plus 32. So, sorry, negative 18 plus 32. So that's 22. 14, and then minus 12, so that's going to give us 2, and then let's see, minus let me write some of this out, minus 32 plus, let's see, 30, 48 minus 12. So that's going to give us minus 4. And then for our third coordinate, that one's easy. Fortunately, that one's just 3, right? 0 plus 0 plus 3, so 3. So hopefully, if we did everything right, the t of v1 was 2 minus 4, 3. So let's check. Is that right? No, it's not right. Almost. Maybe I just made an arithmetic mistake in the second coordinate. So let's see. Oh yes, actually this minus 18 times 2 is minus 36. So that's going to give us. I made 2 arithmetic mistakes. This should have been plus 4, but now that this is 4 smaller, so this comes out to 0. So 2, 0, 3, which is what it should have been. So you can see that this C matrix is doing its job. It's taking coordinates relative to V and turning them into coordinates for the result of the transform relative to the W basis.